Thank you for inviting me to give a keynote at LCTES. Today, I'm going to talk about how to modernize compiler technology. If you look at a compiler, what does a compiler do? It takes a language, a high-level language, and send it to the compiler and produce an assembly language, which is a low-level language. Basically, compilers can view as a translator that goes from one language to another. However, compilers have few special requirements. This translation has to be precise and correct. It has to make sure the semantics of the high-level program is never violated in the translated program. And hopefully, if you're lucky, the translated program will actually run fast, so you want to generate some fast optimized code. So if you look at a compiler, how does it happen? Normally, a compiler takes a high-level language and transform it to intermediate representation. And this intermediate representation is fed through multiple passes. Each part takes this representation, transform it, hopefully a little bit faster, and the combination of all these phases will end up producing a much faster program at the end. I have been working with compilers for a long time now. And when I started in compilers, there were many other systems that look very similar to compilers. So for example, another translation system, a language translation system, is natural language processing. There basically you take the natural language representation, either text or voice, and go through a bunch of very carefully crafted stages to get to the output you want, something like a translated text or textual understanding or whatnot. So that compilers also look very similar. So you take a high-level language, again go through a bunch of translation stages, lower it to a lower level, go through a bunch of stages and produce the code. So that was in the 80s. What has changed? If you look at natural language processing today, it's completely different. What happening today is you take the input and immediately you send it through some kind of neural network. And most of the things necessary and the output is generated through the neural network. On the other hand, if you look at a compiler today, nothing much has changed. The LLVM compiler, one of the state-of-the-art compilers today out there, has almost a similar representation to what we had 30 years ago. So the first interesting thing is what has changed over time in the last 30 years. So first of all, it's very clear we have a lot more computing power available for us. We have faster CPUs, GPU accelerators, lot more memory available, and also cloud computing. And in fact, if you look at natural language processing, it has taken advantage of all these things. Again, in last 30 years, we got access to a lot of new algorithmic techniques. Some of them are very completely new algorithms. Others, because of the computing and memory power available, those algorithms became viable and usable. And finally, there's a lot more data available. 30 years ago, when I started doing compiler, there was no GitHub. If I want to find programs, I have very few benchmarks with. Today, you can find millions of programs out there in open source. So how can compilers take advantage of that? How do you bring the compiler technology to 21st century? First of all, we should start using more compute power. In fact, it's sad to look at compilers today. We don't even take advantage of parallelism. In fact, compilers are the ones who provide parallelism for everybody else, but we don't even eat our own dog food in here. We can use better algorithms. There are algorithms like machine learning based search algorithms that's available, and a lot of compile optimizations is nothing but a search. Can we use those things to make faster compilers or better compilers? And there's a lot more data available today. And good old days, we use something like spec benchmarks to validate the compiler. But today there's so much more data that we can use to make the compiler better or learn the compiler. However, However, developing compilers is not easy. It is becoming harder. First of all, the compiler depends on the program you're targeting and what hardware you're producing the code for. And today there are a lot more different classes of programs out there. And each of those programs, if you want good performance, you do something different for each class. And also we are targeting many hardware platforms today, from GPUs to CPUs to domain-specific accelerators, and getting everything and creating a compiler for all these different program types and all these different hardware is a really hard problem. And constructing these compilers manually, as you saw in the previous slide, it can have a combinatorial explosion, but also there are other disadvantages. First of all, maintaining and developing compiler optimization is very tedious. So if you look at something like LLVM compiler, this huge number of lines of code, thousands of contributors. In fact, it's one of the most complex software systems out there. And also compilers are susceptible to bit rot. When you have that much of a large code base, it's hard to keep changing that. In fact, if you look at Intel x86 architecture, Intel and AMD spend billions of dollars adding new instructions to that architecture. In fact, there are over 3,600 x86 instructions today. However, a LLVM compiler will only generate thousands of them. So all this extra work Intel did to add instructions haven't propagated through the compiler ecosystem to be taken advantage of. Worse, compilers are susceptible to performance modeling, because most of the compiler decisions has to be done through some performance model. In fact, if you look at LLVM performance model, it's created by Sony for AMD hardware, and that this exact same model used for Intel hardware. So even when Intel updated the hardware, not only it's not taking advantage of the hardware, it's using some very old different vendors' machine to basically predict the performance. And this performance we found to be almost 20% error in here. Because of these performance models, the compilers in this sad state where the many interesting and great optimizations implemented in, for example, LLVM, but they're all turned off, even -03. Why? Because the performance models are not that good. In many cases, they can lead to worse behavior, worse performance. So because of that, the optimizations are there, but they're all turned off. If you have better performance model, we might be able to turn them on. So that's the state of the art of modern compilers. So let's go take a look at one compiler optimization, see how it has evolved over the years and how we can evolve it further, and that will give you probably a feel how we can do it for the rest of the compiler. The optimization I want to look at is vectorization. So vectorization was developed for supercomputers in the 80s, and for example something like Cray, and here's a graph in fact from a talk from Seymour Cray. So what Cray compilers were good at is basically if you have a very large vector length, you get really good performance. This graph, what graph shows is if there are straight lines of scalar performance and small vector lengths, the vector machine was not good, but as the vector lengths keep growing, you get really good performance. So you need large vectors to get good performance. So what that means is naturally, to get large vectors, you need to look at entire loops. So vectorization was a technology developed as a loop transformation. And there are a lot of work by legends in compiler field like Kennedy, Padua, and about how to basically vectorize loops and get a good performance. But the hardware changed in the 90s. So for example, AMD and Intel and other companies start introducing these multimedia instructions extensions to x86 and the architectures. They have a very different property. You don't need large vectors. You need very small vectors to take advantage of that. And no startup overhead. So these are like normal instructions. You can issue them. Wide loads go to a separate instruction unit, a separate set of registers to process. So crossing between multimedia execution unit and scale execution unit was basically somewhat costly, but if you can work everything in one execution, you will get really good performance. So the question is, can we do better? When you have modern, newer architecture features, can we do compilers better? So this is where Superword level parallelism came in. This is some of the early work that I did about 20 years ago. The observation there is we only need small amount of parallelism to get these machines going. And you can get that parallelism by not looking at the entire loop but just a loop body. So basically what you can do is look at these instructions that are isomorphic and independent, and basically make the instruction packs and basically vectorize them. So this is simple, and in fact if you don't have enough instructions in a loop, you can just unroll the loop and get probably multiple iterations to do something, and then it's very similar to loop vectorizer. But also there might be certain instructions in the basic block itself. For example, if you're doing RGB calculation, you can vectorize them together, whereas loop vectorizer won't. However, there's something you have to write to get it, which is statement packing. So what we need to do is find isomorphic independent statements to pack together. Let's look at an example. So in this example, I have 6 instructions, 3 division instruction and 3 subtraction instruction. They are all isomorphic. So you can basically pack any of these instructions together. There are 3 possible packs for first 3 instruction and 3 possible packs for last 3 instruction. However, not all vector packs can exist at a time. So if one instruction is in one pack, you don't want to create another pack that has the same instruction. That's just extra overhead and might be even incorrect. So we need to find a strategy to find the most possible packs, because you have choices now. So what choice do I do? So let's again look at this basic block what we have and see what we can do. So let's assume I choose these 2 to pack and also these 2 to pack. Perfectly valid packs, correct? But are they profitable? So if you want to pack these 2, you get this. So you can do this division instruction in vector form, and then you can also load those memory locations using vector instructions. And then you can also do the subtraction, and this one is already loaded. So I don't have to do another load. So I have actually created now 4 vector instructions. Are we done? Are we all set? To get correctness, you have to do a few more things. So for example, if you look at this pack, A3A1, for example, A1 is in a different pack with A2 and A3 is not packed at all. So what you have to do is now you have to unpack A1 out of that pack and repack it with A3 to get the results. For example, A2 is already in a pack, so I have to unpack it, use it in here. So now what I have done is I got a 4 vector instructions, but I have to have overhead of 1 packing and 2 unpacking instructions. So that's this set of choices. However, let's assume I chose a different set. So that means S2, S3 to pack and S4, S5 to pack. What you end up is a much different and more profitable pack. So here you have 5 packs that we can get and only 2 unpacking instructions necessary. So if you compare these 2 strategies, it's very clear the second strategy is much better. So if you look at it, first strategy was in fact a PLDI paper. That's what you get. And the second strategy we believe is the optimal strategy. You can't do better than that. So what you want to do is find these packings, and it's not simple because of course there are a lot of these statements in a basic function, and each statement has n other possibilities to pack it with. So basically all the different packing choices say n to the power n, and in fact this can be mapped into the optimal subset selection problem, which is known to be NP-hard. So now we have NP-hard problem. What can we do? Can we take advantage of modern computing power and better algorithms to basically deal with that? So algorithms so far, for example, algorithms in today LLVM Superword level parallelism is basically greedy algorithm. Grid is nice because it's very fast. You can add additional heuristics, but this heuristic can get complicated and it can miss out many opportunities because most heuristics are local. Can we get a global optimization? Can we use optimization framework? So what we did 2 years ago is this system called GoSLP, which use integer linear programming to do superword level parallelism. But this formulation is very tricky. For example, previously multiple people, including our previous work with Larsen, has tried to do it. What we did was try to formulate using paths. So what that means, in this basic block, we have all these possible paths leading to other paths. So what it looked at is all the possible path combinations and see what's the cost benefit for these paths. So here are 9 possible paths in here. So if you formulate this to choose one path, this is actually encoding complexities to the power 2k. This is extremely high and intractable. In fact, even a small program will take 10-20 hours to converge into a solution. So what we did is look at how do we do better. So one insight is this cost depends only on the locality of this instruction, only the neighbors that basically impacting the cost. So instead of trying to formulate a global problem, can you break it up into a bunch of local problems? So we came up with a newer encoding in GoSLP. So what we look at is each pack separately in here. So by doing that, we can get encoding complexity of k times n squared. So now it suddenly become from exponential to quadratic, and this is a lot more trackable. So let me give you a fast glimpse on how this formulation works. So let's look at these instructions. So what we need to find is candidate packs. So here's a possible pack in here. The first one is not packable because the distance between two loads are too large. It's not adjacent. So to get a vector load, you need to be adjacent. So this is one pack. And these next 3 instructions are all isomorphic and independent. So you can come up with 3 possible packs in here. So what you can assign is a decision variable saying it is 1 if that pack is chosen. So now we have IOLP formulation to that maximize the savings and reducing the cost by packing and unpacking under some constraints. So by solving this system, we will find globally what instructions should be packed together. So we do it for power of 2 and repeat until the vector length is filled. So I will give you a few quick glimpses of how some of these things can be formulated. So first you want to do vector savings. Assume I want to pack this thing. What's the savings of doing this pack? So first of all, there's a vector cost. However, what we're not doing is doing this by scalars. So you have to do 2 scalars otherwise. So that should be the savings. And the savings comes about if we actually vectorize it. That's given by this. So what's a packing cost? So assume we vectorize this, and B1 and B2 are used in S5, S6. So if S5 and S6 is vectorized, I can use this pack. Same thing as X6 and X7. I can use this pack. But if you don't basically vectorize this thing and vectorize either one of the other 2 packs, I actually have to do extra packing. So I'm incurring extra packing cost. So what that means is if you pack S5, S6 or S6, S7, but don't vectorize S3, S4, I have to do additional packing instruction to get that. So that's a cost. So we formulate all these costs of packing, unpacking, and other costs, and also dependencies that you can't violate, and then come up with this nice single system. So by doing this, actually we can get some really nice speedups. So this is the kind of speedup we were able to get in Spec 2006, 2017 and NAS parallel benchmarks. I have to point out this is actually significant speedup. These are not speedup for a single loop. This is for entire benchmark that sometimes have hundreds of thousands of lines of code. And a lot of this code might not be vectorizable, but still we parallelize and vectorize enough to get this performance. To put it in this perspective, if you look at Intel, what it does when it upgrades the processor to the next generation, they get about 25% improvement in these benchmarks. And that's $1 billion investment by thousands of engineers spending a couple of years. And here, by using this system, we were able to get a pretty good performance in a bunch of these benchmarks in here. So I want to compare this LLVM result with ICC, because there's this conventional wisdom that ICC loop vectorizer is much better than LLVM. However, what we found was something very different. ICC scalar baseline is much better than LLVM. So first we turn off all the vectorization, and here's the normalized scalar performance for LLVM. LLVM vectorizer, it gives you some performance improvements to just using the scalar. This is the LLVM vectorizer, both SLP vectorizer and loop vectorizer. However, if you do ICC without vectorization, it blows even the LLVM vectorization performance. Basically, out of 16 out of 20 programs, ICC scalar code is much better. But interestingly, if you use ICC vectorizer, it doesn't add that much performance to these programs. We were surprised by that. So this goes against the conventional wisdom. But now we add GoSLP to the mix. What you see is GoSLP is actually much better than even ICC vectorizer. LLVM basically now gain the ground it lost by the scalar code. So LLM vector code was faster than only 5 programs for the ICC vectorizer vector code. But when you put GoSLP into the mix, it's 11 out of 20 programs LLVM became faster. So I think this is a really good part. So the question is, now we got GoSLP, are we done? So we got this optimal heuristic, but again, we have to handcraft this GoSLP, all those rules and whatnot to get the performance in here. These handcraft compilers are hard to maintain. And as we saw before, compilers are much behind hardware. Even the hardware spend billions of dollars, get new hardware, and the compiler is still not taking advantage of that. So can we remedy this? So can we learn from existing algorithms to basically compile? So if you look at a compiler, as I told you before, compiler basically take one language and mapping it to another language. If you have followed machine learning literature, this looks very similar. Language translation is something that machine learning became very good at. Can you use a neural machine translation? So basically feed a high-level program and then basically get a really optimized code in the other end. Would it be really nice to do this? But there's a small catch. Machine learning systems don't guarantee correctness. If you are going through natural language translation, once in a while getting little bit incorrect translations was not that bad. But not so for programs. You cannot build a compiler and tell a user, say, 99% of the times you get the correct program. Once in a while, we will create incorrect program. No user is going to go for that. Users expect, unfortunately, the compilers to always be correct. So this doesn't work exactly. So what can we do? Another problem actually is the space is pretty large, search space, translation space. But machine learning actually has dealt with large spaces, so that we can use the machine learning power. So inspiration came to us when we saw what AlphaGo did. What's AlphaGo doing? It takes a board and then it basically chose one move and did that move. And it repeated that. So what the machine learning system do is using a Markov decision process, do a single move at a time, and then basically at the end learn some reward function, say was that a good move or not. And that move is always correct because you only choose from valid translations. Can you do that for compiler? So what we did was we looked at this program and said, let's come up with all the valid paths I can basically vectorize at that point. And then choose one of those paths, that's benefits. And then basically we come to a new state and then basically iterate, put that back in again. So your input is a partially vectorized program and say, what's next to do? Find all the possible vector paths and then select one. And then iterate over that until you get the final result. And then basically give it a reward, saying whether this program is fast or slow. So can we map this to a Markov decision process? So if you look at GoSLP, what it has to do is basically train a neural network, given the state of the board, pick the most profitable move it can think that it can make. So it can use reinforcement learning. However, we already have this oracle, GoSLP. First thing is, can we do some imitation learning? Can we build a neural network basically to replicate this oracle and imitate the oracle's behavior? And use that instead of the oracle GoSLP to do the learning in here. So first of all, how do you represent the state? So state can be represented using partially vectorized graph, and you can choose one non-vectorized node and find all the possibilities it can vectorize with. But if you choose one, basically the right thing to do is with A1 basically packed with A2, we can basically translate the graph or mutate the graph into a new graph that has that thing vectorized or packed, and then basically iterate this process. So we use a gated graph neural network to basically feed in this graph and use the Oracle GoSLP to train that neural network. So how do you train this neural network? So we have all these programs we vectorize. So we take these basic blocks of the program and ask GoSLP what are the valid or useful translations you should do. Given this valid set, single selected instruction, what should I basically select to pair it up with? So find all these pairs in here. So what it does is found the state action pairs and fed it to and build a policy network to do that same translation. However, this didn't do that well. The problem was GoSLP always found the best solution. So it always went through this optimal path. How about if the policy network made a mistake? It never knew how to correct if it didn't find the right correction. So sometimes it go really well, get the really good results and imitate GoSLP. Other times it just falls flat because it makes one incorrect move and it can't recover out of that. So in order to do that, we use this known technique called dagger. What dagger does, it takes some of these correct transformations in there, but then it will also select randomly something suboptimal as a translation to do. And then it will give that back to GoSLP and say, okay, I made a suboptimal selection now. Now can we recover? So GoSLP being the optimal solution, saying given that state, how do we get the best outcome? That might not be optimal, but given that, how can do that? And it will find other choices. So we basically fed another set of the state action pairs that were basically corrective actions if you make a mistake. With that, we were able to get a good result. The question is, can we learn? Can we learn something similar to this optimal solution? In fact, we can. So what we are showing here is speed up over LLVM vectorizer. The one is LLVM vectorizer, higher is better. So blue is GoSLP and green is this learn system Vemal. So what we are showing here is, in fact, in many cases that Vemal chose vectorization strategy that in fact is better than GoSLP. And of course, few cases it didn't do well. That's expected in a machine learning system. It doesn't guarantee it, but overall it did a pretty good job. So does it learn? It matches or exceeds performance of GoSLP 5 out of 7 benchmarks, and outperforms LLVM also those benchmarks. So this is really nice But if you have been paying close attention, there's something fishy going on here. We did something, we exceeded the performance of Go SLP. So if you look at this in here, in fact, it's even worse. There were two programs that LLVM was better than Go SLP. And there were three programs that basically Vemal was better than Go SLP. But we told you before that Go SLP was in fact the optimal solution. How can you be faster than the optimal solution? Optimal is supposed to be the best. So let me explain how you can beat the optimal solution. The thing is, when you define optimality, optimality is under some criteria. In here, the optimality is given under a cost model. So the cost model, you can give a linear solver like integer linear programming is a linear cost model. That means the instruction cost get added up. But in a modern day superscalar, the cost is not additive cost model. It's a much more complicated cost model. The cost model is inaccurate. So let me explain the graph to the right of you. So what we have done is look at all the basic blocks of this benchmark suite we had and said how much does vectorization adds. So it depends on how much performance you get. So higher is better. That means 60% means 60% of the instructions or runtime is reduced, and at the other end basically nothing get optimized, so you basically have no improvement. So for all basic blocks we ordered by the SLP vectorizer's performance, so the higher is in the left hand side goes down. So now we run Go SLP next to everything. So what you see is most cases Go SLP is better than the SLP vectorizer, sometimes in large number. But there are certain cases where Go SLP is worse than SLP. So this is because the Go SLP cost model predicted something that is inaccurate and vectorized something that it shouldn't have. Or it didn't vectorize something it should have vectorized, whereas LLVM vectorizer basically figured that one out. So what that means is the cost model matters. So the next, let's look at how we can build accurate cost models. Building accurate cost models are hard. So for example, Intel microprocessor, there are multiple cost models such as LLVM MCA or Intel own IACA cost model. These analytical models that almost simulate the hardware, but they are 20% off from actual results. Why is that? Because what these cost models have to do is, given a basic block, it has to figure out what goes inside this extremely complicated beast that's today's microprocessors and predict the number of cycles it will take. Worse, if you're outside Intel, many things that's happening inside this beast is opaque. There are proprietary things going on, you don't even know what it does. So these predictions become even harder. So what do you have to do? Poor engineers who are building these cost models has to get these Intel manuals and go through these manuals and figure out the cost of each instruction. I'll tell you this is not that easy, because even if you look at one instruction, its cost is not in one place. You can find it in one manual, and then another manual might have added time and say, by the way, if all the inputs are 0, we have this bypass logic that can get the cost to a different level. And you have to have all these things combined together. So in LLVM MCA, all those things put together that describe if each instruction with certain conditions, what the cost model is going to be. So somebody manually did that. This is tedious to develop and maintain. And there's a lot of human error that in fact we reported multiple of those things that get corrected in the MCA cost model. And there's also modeling error. In fact, if you look at the LLVM cost model, it basically models Intel's hardware using a cost model created by Sony for AMD. So it's not even the same family, same vendor's microprocessor that's being used to model the cost. And this is how we basically trying to take advantage of new instructions or even the existing instructions that Intel spent billions of dollars creating by using completely outdated or irrelevant cost model. The question is, can we do better? So can we train a neural network to take a basic block and predict the cost? That's what we did in the ITMR. And what I will show you is this is actually fast and accurate way of predicting cost. So what we need to do is build a neural network, but we are very worried to make this a complicated task for the programmer. So the first thing he said is, we are not asking the programmer to come up with this crazy set of features from the hardware to learn or the instructions to learn. So we just want to feed in just the sequence of instructions. So the neural network we build basically take a sequence of instructions, token embeddings, and the first layer create these embeddings in here. Then it feeds into a first layer of LSTM that come up with intermediate values for each instruction, and then feed that into a next layer to come up with a throughput prediction. We train this using 1.4 million basic blocks taken out of SPEC and NAS parallel benchmarks, and we can get ground truth by actually running it in the certain hardware. However, we had to actually do some work to get correct and repeatable results in running these benchmarks, basic blocks, and then we can basically get the neural network to predict, figure out the error, and train the neural network. So what we're showing here is the results compared to LLVM, MC, and IACA. In fact, ITMR is twice as good as the systems out there today in our prediction. And it's also portable, because if you have new hardware, you don't have to rewrite these 2000 lines of code. We just have to set it up, run it through these basic blocks, collect the numbers, and basically go home at night to train the neural network, and voila, you have a model for this new hardware. So finally, I'm going to talk to you a little bit about, can we learn the full compile optimization stack? So I showed you how to do vectorization. Can we go beyond? So if you look closely at what compilers do, we do three things. First of all, we need to be correct. So what that means is each transformation or each compiler pass has a space of correct transformations. So you have to precisely describe that. You can't just go do incorrect things in here. So there's optimization space of correct transformations. Then there's a compiler strategy that will basically select through this transformation. We have to look at the program, extract some data, look at this space and come up with the right transformation. And the right transformation should be selected through a cost model. And that cost model sometimes is tricky because the transformations is done at high level. So you don't have the full end-to-end cost at that point. You are doing intermediate representation to intermediate representation translation, and you need to know the cost at that level. So what we have worked today is this happy place where all the translations we did, basically we never made any translation that create incorrect program. So we came up with a valid space and basically we searched through that. However, it's not necessary to be there. You can go to the scary place where you let the translation actually make the program incorrect, and then using machine learning and the right cost models and right correctness models basically get back to a perhaps much better but correct coding here. But we haven't gone there, but that's an interesting space to explore. And I'm going to talk about a little bit of these things in next couple of slides. When we are doing this new way of doing compilers, I think there's an opportunity to rethink how we build compiler parsers. We also need really good end-to-end performance predictions to get there. And also I'll talk about how we need robust representations. So let's first look at compiler parsers. Compilers are built using multiple parsers, and in fact we have hypothesized each parse produce a correct program but hopefully a little bit of a better program, and combination of multiple passes basically lead to better final better result. So the way we do this is write individual classes separately. So what happens is each pass look at its translation space, it makes its decision, and it's do transformation. And these passes are independent, except in reality they are all coupled. A decision made in early pass will impact decision done in a later pass. So instead of thinking about this as multiple passes, can we basically combine them together? Can we look at a combined space, a joint optimization space, and also joint decision space on top of that, and then basically map it into transformations. So there's a good opportunity to basically rethink how this compiler transformation should be done here. What are the right transformations? Because original compilers were built because at that time the algorithms available led to those decisions of building passes. For example, instruction scheduling and register allocation. There was a graph coloring algorithm, that means you can build a register allocation pass. And also there was something like list scheduling that you can build a separate instruction scheduling pass. The pass delineation was basically artifact of available algorithms. Now we have a complete new set of algorithms available for us. So can we redo this pass delineation? This is a very exciting thing at this point to think about this. Second, performance prediction. Right now what we are doing is we are predicting a throughput of a basic block. That means we are assuming there's no branches, all memory references are fetched using L1 cache hits, but in reality that is not what happens. Data plays a huge role in performance. So not only one processor, you might have multiple of sockets, each has a very complex memory system that leads to things like branch predictions, cache misses, TLB misses. All these things matters in performance. So how do you go about basically not only looking at the program but look at the data and actually predict the end-to-end performance than just the basic book performance? I think this is extremely important to get this right. And if you can do that, there are a lot more applications you will be useful beyond the compilers, architectures, things like databases, distributed computing, all these things that has make decisions can use prediction of the performance that the decisions can lead to come up with better decisions. So I think this is a very important piece of work to do. The final thing I want to talk about is representation. In the last few years, machine learning has taken the world by storm. Why? Because certain areas found a really good representation. In fact, if you look at image processing and vision, for a long time they were pretty bad. The algorithms were able to do very few things. Like you were comparing what the human can do versus the computers can do, it was pathetic. Then people realized a convolutional neural network is a really good representation of images. And by doing that, you could translate many very important problems. This representation really helped us. Same thing happened in text processing. Recurrent neural network, RNNs, became a good representation, and now transformers, basically suddenly translation, text understanding, natural language processing, all these things became really good using this representation. There are other areas, something like social network, things like graph neural networks suddenly became really good at finding properties of social networks. People figured out interesting representations that represent the important properties of a molecule in this machine learning format, and the minute you do that, there could be many different things, in fact finding new drugs using these machine learning models, because they came up with a really good representation to represent molecules. We still don't have a good representations for programs. Is a graph neural network the right representation? Can we take advantage of global properties in this graph neural network? Some of it possible. Semantic properties, are they represented in the representation? Some, probably not. Is this representation language agnostic? And does it take advantage of dynamic properties? And does this representation knows the difference between a loop goes from 1 to 10, 1 to million? It's a very different, even though textually it looks very similar. If we can come up with a good representation, we think we can do a lot more than automatic program optimization. There are many things we would like to do with programs. And I believe somebody who can come up with this right representation will change how we build compilers drastically. So with that, I'm going to stop, and here's some of the projects in my group. We have been working a lot on domain-specific languages because we believe when you look at a domain, we can understand a lot more to get the high performance needed for each of these domains. We have been also looking at, as this talk showed, how to use modern machine learning technology to basically make compilers faster. There are a lot of other interesting projects going on in my group. Please go take a look at. And also I want to thank all the funders. Thank you very much for listening to my talk and inviting me to come and give this keynote at LCTES. Thank you.